Hello, I'm Diary, a master's course of DTM Lab. The paper I'm going to review today is Dynamic Technology Impact Analysis. First, the bibliographic information of the paper. The paper was published in the journal CIE in 2026, and the keywords and highlights of the paper are as follows. The table of contents for the presentation is as follows. This slide explains the research background and necessary at the study. Technology impact analysis is important because it helps identify the potential influence of technologies on future innovation and industry. Traditionally, expert-based approaches such as DELPI were used, but as technological development has accelerated, data-driven methods have become more important. In particular, patent citations are widely used as indicators of technological value. However, existing models often fail to capture the dynamic changes of the technology impact over time. Therefore, this study emphasizes the need for a framework that can analyze technology impact across different time horizons. So, this study aims to propose a multitask learning approach to dynamically predict patent citation counts across multiple time horizons. It further aims to interpret the changing importance of patent indicators using shape-based explainability analysis. Ultimately, it contributes to both academic research and practical decision making in technology management and R&D planning. So it explains the background of technology impact analysis. Patents are widely used as data sources for analyzing technological impact, and forward citation counts are commonly used as indicators of technological value. Early studies mainly relied on probabilistic models, but this requires sufficient citation accumulation and have limitation in early prediction. Machine learning approaches have recently been used to improve citation prediction. However, most studies treat prediction as a single task problem and don't consider the dynamic relationships between different time horizons. The overall process of the proposed approach encompasses the four discrete steps illustrated in Figure 1. Relevant patents are collected from databases such as the USPTO and stored in a relational database after passing semi-constructed format. The data are categorized into bibliographic, textual, and citation information. Citation data are organized as ATG list to represent technological dependence between patents. In this step, the study defines the patent indicators used to predict technology impact. Through a literature review, a total of 44 indicators were identified to represent technological characteristics observable at the time of patent registration. These indicators are grouped into 6 categories, including scope and coverage, priority, development effort, completeness, technological environment, and prior knowledge. And the study proposes a multitask learning model to predict technology impact across multiple time horizons. Unlike single task or ensemble models, MTL learns several related tasks simultaneously and captures the relationships between different time horizons. This approach allows the model to predict technology impact even using early-stage patent indicators. The proposed MTL architecture consists of input, shared, and task-specific layers. The shared layers learn common representations across tasks, while the task-specific layers optimize predictions for each time horizon. The model then outputs probabilistics for each impact level and is trained by minimizing the weighted loss across all tasks. In this step, the study evaluates the performance of the proposed model using several metrics to address class imbalance and ensure robust evaluation. Additional metrics. After evaluating the model performance, shape analysis was applied to interpret the result. This allows the identification of the key patent indicators that influence technology impact across different time horizons and provides insight into how technology impacts evolve over time. In this step, the authors conducted a case study on battery technology because it plays a key role in industries such as electronic vehicles and renewable energy. For the analysis, patents classified under IPC H01M were collected. To examine whether technology impact changes over time, four citations were tracked over 3, 5, and 10 years horizons. The results show that citation distributions are highly skewed, with only a small number of patents receiving many citations. Based on citation counts, patents were categorized into breakthrough, valuable, and moderate technologies. The analysis also identified different dynamic patterns such as sustained impact, peak and fade, and late blooming patterns. These results confirm that technology impact varies significantly over time. This section examines whether technology impact across different time horizons influence each other. To address this question, the authors applied a multitask learning model that shares knowledge across short, mid, and long-term prediction tasks. The model was trained using 8,454 patents and tested on 2,397 patents, and its performance was evaluated using five-fold cross-validation. The results show that the MTL model consistently outperformed the single task running model. In particular, it improved the identification of valuable and breakthrough technologies under class imbalance. The performance improvement was most noticeable in midterm forecasting, indicating that sharing information across time horizons helps improve prediction accuracy. This section analyzes why technology impact changes over time using deep shape analysis. The goal is to identify which patent indicators influence breakthrough technology predictions across different time horizons. The results show that the important determinants vary depending on the time horizon. Short-term impact is mainly influenced by scientific knowledge and technology recombination, while mid-term impact is related to growth, speed, and technological breadth. For long-time impact, scientific knowledge, technological breadth, and international priority range play important roles. Among these indicators, scientific knowledge consistently shows a strong positive influence on breakthrough technologies, especially in the long term. In contrast, dependence on homogeneous technologies negatively affects a long-term technology impact. Case analysis confirms that the patents with strong prior knowledge, broad technological references, and international protection strategies are more likely to achieve sustained high impact. Conversely, low impact patents tend to show weaker international positioning and less strategic knowledge structure. Finally, axiomatic explanational consistency test demonstrate that the shape interpretations are robust and consistent across time horizon. This is the discussion and validation of the proposed approach. First, the authors validated the model by examining whether predict breakthrough technologies show higher patent quality indicators. The results show that patents predict to have higher impact tend to have longer maintenance period, more technology transfer cases, and larger patent family size. This indicates that the model's predictions are statistically consistent with real patent value indicators. In addition, the proposed approach was combined with topic modeling using both topic to identify 22 battery technology subdomains. The results show that energy storage devices consistently demonstrate the highest technology impact, while some fuel cell related technologies showed relatively lower impact. These findings demonstrate that the proposed approach can also be applied to analyze technology impact at the field level. This section discusses the interpretability of the model and implications for feature selection. The study used 44 patent indicators, although some redundancy and correlations may exist because these variables originate from the patent application process. The MTR model can mitigate these correlations by learning layered representations and allowing feature importance to vary across different time horizons. The analysis also identified several low importance features. However, the others emphasized that this does not necessarily mean these indicators should be excluded because the importance of features may vary depending on the technological domain. Finally, the study proposes a multitask learning framework to predict time variant technology impact across different time horizons. The case study on battery technology shows that patent impact evolves over time and that modeling cross-horizon relationships improves prediction performance compared to single-task models. In addition, shape analysis helps explain how key indicators influence technology impact across different horizons. From an academic perspective, this study introduced temporal multitask modeling to early-stage patent impact prediction. From a practical perspective, the approach can support IP strategy, technology valuation, and R&D planning. However, the study mainly relies on citation-based indicators, which may not fully capture multidimensional technology value. Therefore, future research could incorporate textual and network-based features, additional value indicators. This is end of the presentation. Thank you for listening.